Colossus was the world's first electronic digital computer that was at all programmable. The Colossus computers were developed for British codebreakers during World War II to help in the cryptanalysis of the Lorenz cipher. Without them, the Allies would have been deprived of the very valuable military intelligence that was obtained from reading the vast quantity of encrypted high-level telegraphic messages between the German High Command and their army commands throughout occupied Europe. Colossus used thermionic valves to perform Boolean operations and calculations. Colossus was designed by the engineer Tommy Flowers to solve a problem posed by mathematician Max Newman at the Government Code and Cipher School at Bletchley Park. Alan Turing's use of probability and cryptanalysis contributed to its design. It has sometimes been erroneously stated that Turing designed Colossus to aid the cryptanalysis of the Enigma. Turing's machine that helped decode Enigma was the electromechanical Bombe, not Colossus. The prototype, Colossus Mark I, was shown to be working in December 1943 and was operational at Bletchley Park by February 5, 1944. An improved Colossus Mark II that used shift registers to quintuple the speed, first worked on June 1, 1944, just in time for the Normandy landings. 10 Colossi were in use by the end of the war. The destruction of most of the Colossus hardware and blueprints, as part of the effort to maintain a project secrecy that was kept up into the 1970s, deprived most of those involved with Colossus of credit for their pioneering advancements in electronic digital computing during their lifetimes. A functioning replica of a Colossus computer was completed in 2007 and is on display at the National Museum of Computing at Bletchley Park. Purpose and origins. The Colossus computers were used to help decrypt radio teleprinter messages that had been encrypted using the electromechanical Lorenz SZ40/42 inline cipher machine. To encipher a message with the Lorenz machine, the 5-bit plaintext characters were combined with a stream of key ciphertext characters using the XOR Boolean function. This is a NAM cipher, and the deciphering process involved an identically set-up Lorenz SZ machine generating the same key sequence and XORing it with the received ciphertext to reproduce the plaintext. The key stream was generated using 12-pin reels. British codebreakers referred to encrypted German teleprinter traffic as fish, and called the SZ40/42 machine and the intercepted messages tunny. Colossus was used for finding possible Lorenz key settings not completely decrypting the message. It compared two character streams, counting a statistic based on a programmable Boolean function. The ciphertext was read at high speed from a paper tape. The other stream was generated internally, and was an electronic simulation of part of the Lorenz machine. If the count for a setting was above a certain threshold, it would be sent as output to an electric typewriter. The logical structure of the Lorenz machine was diagnosed at Bletchley Park without a machine being seen, something that did not happen until almost the end of the war. First, John Tildeman, a very talented GC&CS cryptanalyst, derived a key stream of almost 4,000 characters from a German operating blunder in August 1941. Then Bill Tutt, a newly arrived member of the research section, used this key stream to work out the logical structure of the Lorenz machine. He correctly deduced that it had 12 wheels in two groups of 5, which he named the I and I wheels, and the remaining two the I 1/4 micron or motor wheels. The chi wheels stepped regularly with each letter that was encrypted, while the psi wheels stepped irregularly, under the control of the motor wheels. In order to decrypt the ciphertext of the transmitted messages, there were two tasks that had to be performed. The first was wheel breaking, which was the discovery of the pin patterns for all the wheels. These patterns were set up once on the Lorenz machine and then used for a fixed period of time and for a number of different messages. The second task was wheel setting, which could be attempted once the pin patterns were known. Each message encrypted using Lorenz was enciphered at a different start position for the wheels, and it was this start position of the chi wheels that Colossus was initially designed to discover. The XOR function used in the NAM cipher for both enciphering and deciphering could also be used to upset the cipher's obscuring of the characteristics of the plaintext in the ciphertext. This was discovered by Alan Turing in July 1942 when he was on loan from the German Naval Enigma section to the research section at Bletchley Park. He was studying tunneling and invented a method of wheel breaking that became known as Turingery. With a truly random key, the Bombe cipher removes the natural language property of a plaintext message of having an uneven frequency distribution of the different characters, to produce a uniform distribution in the cipher text. Turing worked out that if, instead of examining the frequency distribution of the characters in the cipher text, examining the character-to-character changes of character streams showed a departure from uniformity which provided a way into the system. Providing the character-to-character changes was achieved by differencing in which each bit or character was XORed with its successor. By using differencing and knowing that the psi wheels did not advance with each character, Tut worked out that trying just two differenced bits of the chi stream against the differenced cipher text would produce a statistic that was non-random. This became known as Tut's 1+2 break-in. The process of wheel setting found the start position of the key wheels in relation to the start of the message. Initially Colossus was used only to work out the start positions of the chi wheels, but later, methods were devised for the other wheels. Later still an additional electronic unit was designed for wheel breaking, which was added to some Mark II Colossi. The manual processes and decrypting messages were undertaken in a section at Bletchley Park led by Major Alf Tester which was known as the testry. Colossus was developed for the Newmanary, the section headed by the mathematician Max Newman at Bletchley Park responsible for machine methods against the Lorenz machine. The Colossus design arose out of a prior project that produced a counting machine dubbed Heath Robinson. The main problems with Heath Robinson were the relative slowness of electromechanical parts and the difficulty of synchronizing two paper tapes, one punched with the encrypted message, the other representing the patterns produced by the wheels of the Lorenz machine. The tapes tended to stretch when being read, at some 2,000 characters per second, resulting in unreliable counts. Design and construction. Tommy Flowers was a senior electrical engineer at the Post Office Research Station at Dollis Hill who had been appointed MBE in June 1943. Prior to his work on Colossus, he had been involved with GC&CS at Bletchley Park from February 1941 in an attempt to improve the bombs that were used in the cryptanalysis of the German Enigma cipher machine. He was recommended to Max Newman by Alan Turing who had been impressed by his work on the bombs. The main components of Colossus's predecessor, Heath Robinson were as follows. A tape transport and reading mechanism that ran the looped key and message tapes at between 1,000 and 2,000 characters per second. A combining unit that implemented the logic of Tut's method. A counting unit that had been designed by Dr. C. Ewan Williams of the Telecommunications Research Establishment at Malvern which counted the number of times the logical function returned a specified truth value. Flowers had been brought in to design the Heath Robinson's combining unit. He was not impressed by the system of a key tape that had to be kept synchronized with the message tape and, on his own initiative, he designed an electronic machine which eliminated the need for the key tape by having an electronic analog of the Lorenz machine. He presented this design to Max Newman in February 1943, but the idea that the 1 to 2,000 thermionic valves proposed could work together reliably was greeted with great skepticism. So more Robinsons were ordered from Dollis Hill. Flowers, however, knew from his pre-war work that most thermionic valve failures occurred as a result of the thermal stresses at power-up, so not powering a machine down, reduced failure rates very substantially. Flowers persisted with the idea and obtained support from the director of the research station, W. Gordon Radley. Flowers and his team of some 50 people in the switching group, spent 11 months from early February 1943 designing and building a machine that dispensed with the second tape of the Heath Robinson, by generating the wheel patterns electronically. This prototype, Mark I Colossus performed satisfactorily at Dollis Hill on December 8, 1943, and was taken apart and shipped to Bletchley Park, where it was delivered on January 18 and reassembled by Harry Fensom and Don Hawood. It attacked its first message on February 5, 1944. As it was a large structure it was quickly dubbed Colossus by the WRNS operators. This machine contained 1,600 thermionic valves and was soon followed by an improved production Mark II machine. 9 of this version of the machine were constructed, the first being commissioned on June 1, 1944. after which Alan Coombs took over leadership of Colossus production. The original Mark I machine was converted into a Mark II, and an 11th Colossus was essentially finished when the war in Europe ended. The main units of Flower's design were as follows. A tape transport and photoelectric reading mechanism very similar to Heath Robinson's. A coder and adder that simulated the Lorenz machine using thyratron rings. A logic unit that performed Boolean operations. A master control that contained the electronic counters. A printer. Most of the design of the electronics was the work of Tommy Flowers, assisted by William Chandler, with Sidney Broadhurst working on the auxiliary electromechanical parts. The Mark II Colossus was designed while Mark I was being constructed. It contained 2400 valves and was both 5 times faster and simpler to operate than the original version. Flowers overcame the problem of synchronizing the electronics with the message tape by generating a clock signal from the reading of the sprocket holes of the message tape. The speed of operation was thus limited by the mechanics of reading the tape. The tape reader was tested up to 9700 characters per second before the tape disintegrated. So 5000 characters second 40 a foot per second was settled on as the speed for regular use. The Mark II Colossus included the first ever use of what would now be called shift registers and systolic arrays, enabling 5 simultaneous tests, each involving up to 100 Boolean operations, on each of the 5 channels of the punch tape. This gave an effective processing speed of 25,000 characters per second. Operation. Colossus used state-of-the-art vacuum tubes, thyratrons and photomultipliers to optically read a paper tape and then applied programmable logical functions to the bits of the key in ciphertext characters, counting how often the function returned true. Colossus was designed to perform the task of wheel setting, that is determining the start point of the stream of key characters in relation to the characters of the encrypted message on the paper tape loop. Initially it was only the I wheels that were examined. To keep the size of the task manageable, only 2 bits of the chi stream were examined in the first run, then progressively the other bits. Success at this stage allowed the production of a version of the ciphertext from which the chi component of the key had been removed, the so-called dead chi. This transformation allowed manual methods to be used to work out the settings of the I and I1/4 micron motor wheels. Later, Colossus was used for determining the settings of the psi wheels. All of this required that wheel breaking, the discovery of the pin patterns for all the wheels, had been successfully achieved. Later Mark II Colossi were equipped with a special unit to achieve this as well. Programming Colossus was by setting switches and plugging appropriate units together. Sometimes, 2 or more Colossus computers tried different possibilities simultaneously in what now is called parallel computing, speeding the decoding process by perhaps as much as double the rate of comparison. Influence and fate. Colossus was the first of the electronic digital machines with programmability, albeit limited by modern standards. It had no internally stored programs. To set it up for a new task, the operator had to set up plugs and switches to alter the wiring. Colossus was not a general-purpose machine, being designed for a specific cryptanalytic task involving counting and Boolean operations. A Colossus computer was thus not a fully general Turing-complete machine. However, Professor Benjamin Wells of the Departments of Computer Science and Mathematics, University of San Francisco, has shown that a universal Turing machine could have been run on the set of 10 Colossus computers. This means that Colossus satisfies the definition of Turing-complete given in the Wikipedia article Turing completeness. Most of the other computing machines of this era were also not Turing-complete, or the first designs of Konrad Zuse. The notion of a computer as a general-purpose machine that is, as more than a calculator devoted to solving difficult but specific problems did not become prominent until after World War II. Colossus was preceded by several computers, many of them first in some category. Zuse's Z3 was the first functional fully program-controlled computer, and was based on electromechanical relays, as were the Bell Labs machines of the late 1930s. The Atanasoff Berry computer was electronic and binary but not programmable. Assorted analog computers were semi-programmable. Some of these much predated the 1930s. Babbage's analytical engine design predated all these. It was a decimal, programmable, entirely mechanical construction but was only partially built and never functioned during Babbage's lifetime. Colossus was the first combining digital, programmable, and electronic. The first fully programmable digital electronic computer was the ENIAC, which was completed in 1946. The use to which the Colossus computers were put was of the highest secrecy, and the Colossus itself was highly secret, and remained so for many years after the war. Thus, it could not be included in the history of computing hardware for many years, and Flowers and his associates were deprived of the recognition they were due. Being not widely known, Colossus had little direct influence on the development of later computers. It was EDVAC that was the early design which had the most influence on subsequent computer architecture. However, the technology of Colossus, and the knowledge that reliable high-speed electronic digital computing devices were feasible, did have a significant influence on the development of some early computers in the United Kingdom and probably in the US. A number of people who were associated with the project and knew all about Colossus played significant roles in early computer work in the UK. In 1972, Hermann Goldstein wrote that Britain had such vitality that it could immediately after the war embark on so many well-conceived and well-executed projects in the computer field. In writing that, Goldstein was unaware of Colossus, and its legacy to those projects of people such as Alan Turing, and Max Newman and I.J. Good. Brian Randall later wrote that the Colossus project was an important source of this vitality, one that has been largely unappreciated, as has the significance of his places in the chronology of the invention of the digital computer. Colossus documentation and hardware were classified from the moment of their creation and remained so after the war, when Winston Churchill specifically ordered the destruction of most of the Colossus machines into pieces no bigger than a man's hand. Tommy Flowers was ordered to destroy all documentation and burned them in a furnace at Dollis Hill. He later said of that order, "That was a terrible mistake. I was instructed to destroy all the records, which I did. I took all the drawings and the plans and all the information about Colossus on paper and put it in the boiler fire. And saw it burn. Some parts, sanitized as to their original use, were taken to Newman's Royal Society Computing Machine Laboratory at Manchester University. The Colossus Mark I was dismantled and parts returned to the post office. 2 Colossus computers, along with 2 replica Turing machines, were retained, moving to GCHQ's new headquarters at Eastcote in April 1946, and moving again with GCHQ to Cheltenham between 1952 and 1954. One of the Colossi, known as Colossus Blue, was dismantled in 1959. The other in 1960. In their later years, the Colossi were used for training, but before that, there had been attempts to adapt them, with varying success, to other purposes. Jack Good relates how he was the first to use it after the war, persuading NSA that Colossus could be used to perform a function for which they were planning to build a special-purpose machine. Colossus was also used to perform character counts on one-time pad tape to test for non-randomness. Throughout this period the Colossus remained secret, long after any of its technical details were of any importance. This was due to the UK's intelligence agency's use of Enigma-like machines which they promoted and sold to other governments, and then broke the codes using a variety of methods. Had the knowledge of the code-breaking machines been widely known, no one would have accepted these machines. Rather, they would have developed their own methods for encryption, methods that the UK services might not have been able to break. The need for such secrecy ebbed away as communications moved to digital transmission and all digital encryption systems became common in the 1960s. Information about Colossus began to emerge publicly in the late 1970s, after the secrecy imposed was broken when Group Captain Winterbotham published his book The Ultra Secret. More recently, a 500-page technical report on the Turing cipher and its cryptanalysis entitled General Report on Turing was released by GCHQ to the National Public Record Office in October 2000. The complete report is available online, and it contains a fascinating paean to Colossus by the cryptographers who worked with it. it is regretted that it is not possible to give an adequate idea of the fascination of a Colossus at work. Its sheer bulk and apparent complexity. The fantastic speed of thin paper tape round the glittering pulleys. The childish pleasure of knot, span, print main header and other gadgets. The wizardry of purely mechanical decoding letter by letter. The uncanny action of the typewriter in printing the correct scores without and beyond human aid. The stepping of the display. Periods of eager expectation culminating in the sudden appearance of the longed-for score. And the strange rhythms characterizing every type of run, the stately break-in, the erratic short run, the regularity of wheel braking, the stolid rectangle interrupted by the wild leaps of the carriage return, the frantic chatter of a motor run, even the ludicrous frenzy of hosts of bogus scores. Reconstruction. Construction of a fully functional replica of a Colossus Mark II was undertaken by a team led by Tony Sale. In spite of the blueprints and hardware being destroyed, a surprising amount of material survived, mainly in engineers' notebooks, but a considerable amount of it in the US. The optical tape reader might have posed the biggest problem, but Dr. Arnold Lynch, its original designer, was able to redesign it to his own original specification. The reconstruction is on display, in the historically correct place for Colossus No. 9, at the National Museum of Computing, in H Block Bletchley Park in Milton Keynes, Buckinghamshire. In November 2007, to celebrate the project completion and to mark the start of a fundraising initiative for the National Museum of Computing, a cipher challenge pitted the rebuilt Colossus against radio amateurs worldwide in being first to receive and decode 3 messages enciphered using the Lorenz SZ42 and transmitted from radio station Del OHNF in the Heinz Nixdorf Museum's Forum Computer Museum. The challenge was easily won by radio amateur Joachim Th, who had carefully prepared for the event and developed his own signal processing and code-breaking code using Ada. The Colossus team were hampered by their wish to use World War II radio equipment, delaying them by a day because of poor reception conditions. Nevertheless, the victor's 1.4 GHz laptop, running his own code, took less than a minute to find the settings for all 12 wheels. The German code breaker said, "My laptop digested ciphertext at a speed of 1.2 million characters per second, euro 240 times faster than Colossus." If you scale the CPU frequency by that factor, you get an equivalent clock of 5.8 MHz for Colossus. That is a remarkable speed for a computer built in 1944. The Cypher challenge verified the successful completion of the rebuild project. On the strength of today's performance, Colossus is as good as it was 6 decades ago, commented Tony Sale. We are delighted to have produced a fitting tribute to the people who worked at Bletchley Park and whose brain power devised these fantastic machines which broke these ciphers and shortened the war by many months. See also, History of computing hardware, list of vacuum tube computers, Lorenz cipher, supercomputer, Z3, Z4, footnotes. References. Further reading, Colossus, Creating a Giant on YouTube. A short film made by Google to celebrate Colossus and those who built it, in particular Tommy Flowers. Cragen, Harvey G., From Fish to Colossus, How the German Lorenz cipher Was Broken at Bletchley Park, Dallas, Cragen Books, ISBN A0-9743045-0-6AA. A detailed description of the cryptanalysis of Turing, and some details of Colossus, Never, Ted, Britain's best-kept secret, Ultra's base at Bletchley Park, Sutton Publishing, Gloucestershire, ISBN A978-0-7509-2355-2AA. A guided tour of the history and geography of the park, written by one of the founder members of the Bletchley Park Trust, Gannon, Paul, Colossus, Bletchley Park's Greatest Secret, Atlantic Books, ISBN A978-1-84354-331-2. Rojas, R. Hashajan, U. The First Computers, History and Architectures, MIT Press, ISBN A0-262-18197-5AA. Comparison of the first computers, with a chapter about Colossus and its reconstruction by Tony Sale. Sale, Tony, The Colossus Computer 1943–1996, How It Helped to Break the German Lorenz Cipher in WWII, Kidderminster, M. and M. Baldwin, ISBN A0-947712-36-4, a slender booklet, containing the same material as Tony Sale's website. Smith, Michael, 1998, Station X, The Codebreakers of Bletchley Park, Pan Grand Strategy Series, London, Pan Macmillan Limited, ISBN A978-0-330-41929-1. Other meanings: there was a fictional computer named Colossus in the movie Colossus, The Forbin Project. Also see List of fictional computers. Neil Stephenson's novel Cryptanalysis also contains a fictional treatment of the historical role played by Turing and Bletchley Park. External links: The National Museum of Computing, Tony Sale's Codes and Ciphers contains a great deal of information, including Colossus, The Revolution in Code Breaking, Lorenz Cipher and the Colossus, The Machine Age Comes to Fish Code Breaking, The Colossus Rebuild Project, The Colossus Rebuild Project, Evolving to the Colossus Mk2 Walk-Around Colossus, a detailed tour of the replica Colossus. Make sure to click on the more text links on each image to see the informative detailed text about that part of Colossus. IEEE lecture. Transcript of a lecture Tony Sale gave describing the reconstruction project. BBC News article reporting on the replica Colossus. BBC News article, Colossus cracks codes once more. BBC News article, BBC News article, Bletchley's code cracking Colossus with video interviews February 2, 2010, website on Copeland's 2006 book with much information and links to recently declassified information. Was the Manchester baby conceived at Bletchley Park? Walkthrough video of the Colossus rebuild at Bletchley Park on YouTube.